All right, we're continuing with Chapter 8 in the statistics textbook. Chapter 8 is on correlation between two or more variables, or you can think about this as two or more sets of data, so two or more lists of numbers, to where in part 2 with histograms and the normal curve, we were dealing with one variable, one set of numbers. Now we're thinking about statistically analyzing relationships between two or more variables or two or more lists of numbers. Now we're starting with just looking at analyzing two lists of numbers, two variables. And in the previous section, we talked about the scatter plot, the scatter diagram, where you can graphically illustrate the relationship between two variables. Now in this section, we're going to talk about the correlation coefficient. So in the previous section, we talked about the idea of a strong or weak association between two variables. And this was just based on if there's a strong association between the two variables, then knowing one variable, like, we were talking about fathers versus sons' heights, then knowing like a father's height, if there's a strong association, then you're able to predict the corresponding son's height accurately if there's a strong association. If there's a strong association, knowing one parameter, you have a good ability to predict what the other parameter will be. Now, we mainly looked at the idea of a strong association from the perspective of a 45-degree line. So if the data points, the better they hugged the 45-degree line, then the stronger or weaker the association. However, when it comes to being able to, if you know one parameter, you can predict the other parameter. It doesn't have to be a 45-degree line. It could be any line, right? Because we can write the equation for a line. So if the data points hugged a line like this, well, that's a strong association. But not even just a line. If the data points hug like a parabolic curve or like an exponential curve or anything, any kind of function or equation that we can write out, you can think of that as a strong association, because you can, if you have one parameter, you have the ability to predict what the other parameter will be. It's just when they're just kind of randomly spread out all over the place, that's when you think about a weak association. Now, however, what we're going to do is, when we're thinking about relationships between variables, one of the basic ways to quantify how related two variables are or how well they correlate is with something called the correlation coefficient. And the correlation coefficient is based on seeing how well the data hugs a line, but not just a 45-degree line, a line oriented in any way. This is the basic way you can see how well two data sets are correlated. Now you might say, well, wait a minute, what if you have a data set that looks like this? It could be exponential. Well, that's not going to hug a line very well, so it's not, the correlation coefficient is not going to say that these data points are correlated very well, even though they are. Yeah, that's true. And so there's going to be other ways that we can test outside of just linear how well two data sets are correlated. Or another way you can say correlated is how strongly associated they are. If you know information about one parameter, you can predict the other. However, we start with the basic definition, the first fundamental way you would look at how well two data sets are associated, or two variables are associated or correlated, is with just we call the correlation coefficient, which is testing for any kind of linear relationship. That's the first fundamental analysis we're going to do to test correlation or association between variables. Okay, so it says, suppose you are looking at the relationship between two variables and have already plotted the scatter diagram. The graph is a football-shaped cloud of points. How can it be summarized? So yeah, we're trying to do something to point out here is that in part two, we did descriptive statistics. We were applying, we had a list of data points, and we were coming up with these parameters that described those list of data points, like these personality traits, the average, the standard deviation, range, etc. Well, it's not like we're done with descriptive statistics. We can still use descriptive statistics in the context of relationships between variables. That's what a correlation coefficient is going to be. So just want to point that out. These are still descriptive statistics. Remember, descriptive statistics are just it's personality traits about data. A correlation coefficient. It's like a parameter you can evaluate that describes a set of data, multiple sets of data, or a relationship between multiple sets of data. Inferential statistics is just we're making predictions. Is all. It's inference. We're saying we expect. It's like probabilities. We expect that we're making a guess. We've come up with some statistics. Now we're going to make a guess. We're coming up with an inference for something. Okay, so but what they're saying is if we have a scatter diagram, the graph is a football-shaped cloud of points, how can it be summarized? Well, okay, what descriptive statistics can we apply to it? The first step would be to mark a point showing the average of the x values and the average of the y values. Okay, so we talked about that. That was very interesting. We can still apply the descriptive statistics that we learned in part two to the analysis of multiple variables at the same time. We can think about the average of one data set, the average of the other data set. And like they said here, you can plot the average of y. You can come up with the average of the y variables, the average of the x variables. So we're still using descriptive statistics here. And there's a coordinate of the two averages, right? That's interesting. That's a descriptive statistic here. The coordinate location on the scatter plot of the averages of the two data sets, the two variables. This is the point of averages, which locates the center of the cloud. Okay, the point of averages. The next step would be to measure the spread of the cloud from side to side. This can be done using the standard deviation of the x values, the horizontal standard deviation, okay? So most of the points will be within two horizontal standard deviations on either side of the point of averages. In the same way, the standard deviation of the y values, the vertical standard deviation, can be used to measure the spread of the cloud from top to bottom. Most of the points will be within two vertical standard deviations above or below the point of averages. So that's another way we can analyze this. You have the point of averages. You can think about how most of the points, like it's hard to say what the exact width or height of the cloud is, right? You can't come up with an exact width or height. Well, one way you could look at that is it's two standard deviations on either side of the point of averages wide and two standard deviations on either side of the vertical side of the point of averages tall. Okay, so now we're applying some descriptive statistics to this analysis of the relationship between two variables, the scatter plot here. All right, so far the summary statistics are the average of the x values, the standard deviation of the x values, the average of the y values, the standard deviation of the y values. These statistics tell us the center of the cloud and how spread out it is, both horizontally and vertically. But there is still something missing. The strength of the association between the two variables, right? How strongly associated are they? Look at the scatter diagram in figure 5. So, okay, it says, let's see. Well, let's come here first. Both clouds have the same center and show the same spread, horizontally and vertically. Okay, so if we come here, both clouds show the same center of averages and the same spread, horizontally and vertically. So that's what they're saying. Something's missing, right? But these still are different. So what are we missing here? Okay. However, the points in the first cloud are tightly clustered around a line. There's a strong linear association between the two variables. In the second cloud, the clustering is much looser. The strength of the association is different in the two diagrams. To measure the association, one or more summary statistics is needed. The correlation coefficient. This coefficient is usually abbreviated as R for no good reason, although there are two R's in correlation. Okay, so if we come back here, if we look at a difference between these two, past just the point of averages and the spread, horizontal and vertical spread, this is more tightly clustered around a line than this. Okay, and so to come up with a descriptive statistic for this attribute, we use the correlation coefficient, which is going to just to note this isn't about the how tightly the data points are around a 45-degree line. It's any line. So it would be that they're saying, so it's any line. Now, again, if you're like me, you might be thinking, well, okay, we could have two data points like this, two sets of data points here that they have the same point of averages, they have the same horizontal and vertical spread, but one looks like this, and the other it's the exact same idea, except instead of following a line, they follow like an exponential. So why is the correlation coefficient just based on a line? Shouldn't it be, how well do they correlate with respect to any of the fundamental types of functions we can make? Well, you could just look at this as this is the first most fundamental way we analyze correlation or association from a linear perspective, because there's an infinite number of functions you could make. You could combine an exponential with a linear function, right? You could do f of x is equal to a e to the x plus bx, right? Maybe it follows this closely, this exponential and linear term combined together. So there's an infinite number of functions you can make. So it's hard to say what's from that kind of perspective, it's hard to say what the association is in general, right? Because again, we could combine a logarithm, a log of x plus bx squared plus c e to the x. Maybe it follows this closely. So how would you make an official statement about a correlation or association for just in general for any kind of function? So the starting point is, look, how well are they correlated from a linear perspective? That's the fundamental way we look at this, okay? So when you hear correlation, the correlation coefficient, it's talking about linear. It's talking about linear, all right? Now, if we come back here, the correlation coefficient is abbreviated as R, so this is the correlation coefficient. That's the normal way you do it. And it says there's no real reason for this, good reason for this. Think about it maybe that there's two R's in correlation. So the correlation coefficient is a measure of linear association or clustering around a line, any line, not just a 45-degree line. The relationship between two variables can be summarized by, so the average of the x values, the standard deviation of the x values, the spread of the x values, average of the y values, standard deviation of the y values. So the point of averages and then the spread around those horizontally and vertically, and the correlation coefficient, R, right? In this case here, where the data points are they are following like a line, those, what would that be? 5 data points, the two averages, the point of averages, the standard deviation, the spread, horizontal and vertical spread around the point of averages, and the correlation coefficient would perfectly describe, well, maybe not perfectly, I guess you could go as far as you want to go, but they would really strongly paint the picture of these two data sets, those parameters, right? Okay. The formula for computing R will be presented in section 4, but right now we want to focus on the graphical interpretation. Figure 6 shows 6 scatter diagrams for hypothetical data, each with 50 points. So I don't have to keep switching pages. Let me bring figure 6 here. Okay, so here's figure 6. So, okay, there's 6 scatter diagrams for hypothetical data, each with 50 points. Okay, the diagrams were generated by computer. In all 6 pictures, the average is 3, and the standard deviation is 1 for x and y. The computer has printed the value of the correlation coefficient over each 6 diagrams. The one at the top left shows a correlation of 0. The cloud is completely formless. As x increases, y shows no tendency to increase or decrease. It just straggles around. Okay, so this is really interesting. We've got these 6 scatter plots. All of these have 50 data points, and all of these have the same point of averages, okay, but they also have the same spread around the point of averages in both the horizontal and vertical direction. So all of these have the same point of averages, and they have the same spread around the point of averages in both directions. So is that enough to describe these data sets? Well, no, look, they're different, right? They're different. But we can use the correlation coefficient to fill in that gap. And in particular, the correlation coefficient is going to be really useful if the data points are the type of function they're following is something linear. If it's not linear, we can still use the correlation coefficient and just to give us some information, but we'll have to think about better ways to, if these were like exponentially distributed, closely, right? They were kind of, as they tightened up, they were going along some direction like this, some sort of like exponential. Then we have to come up with a kind of a better way to think about, to analyze how well they're correlated. But even in this case, we still might be able to make use of the correlation coefficient to point us in a direction. Okay, but so they're saying we're not calculating the coefficient, the correlation coefficient in this section. We just want to get an idea of it. So here the correlation coefficient is 0, and then the correlation coefficient increases all the way to the last graph. And so the more tightly, the better the association, the stronger the association, the higher the correlation coefficient is going to be. And vice versa. So here the correlation coefficient is 0, which presumably would be as low as it can get. So there's like no association here. We can't draw a line in any direction that hugs these data points. They're not correlated. We can't, if we have if we have like one X value or one Y value, we can't make any prediction about if we have an X value, what the Y value is, or if we have a Y value, what the X value is. Even though this has the same point of averages and horizontal and vertical spread as this. It's really interesting. Okay, but as the correlation coefficient increases, they're more tightly clustered, right? And it's looking like we can assume that it looks like the correlation coefficient goes from 0 to 1. 1 is like the best correlation you can get. 0 is the worst, right? This is close to 1, so here, there's a strong association, linear association. If you have information about an X value, you can predict what the Y value is going to be, right? And now, just again, though, if you had like a potential logarithmic, it could be a logarithmic association. Does that mean we can't use the correlation coefficient? Well, that's just something we're going to have to talk about. Maybe we could. That would give us a pretty good idea of what that's something we have to experiment with. Okay. So, yeah, they start off by talking about the correlation coefficient of 0. The cloud is completely formless. As x increases, y shows no tendency to increase or decrease. It just straggles around. The next scatter diagram has r equals 0.40. A linear pattern is beginning to emerge. The next one, r is equals 0.6, with a stronger linear pattern, and so on through the last one. The closer r is to 1, the stronger is the linear association between the variables. And the more tightly clustered are the points around a line. A correlation of 1, which does not appear in the figure, is often referred to as a perfect correlation. All the points will lie exactly on a line. Okay. So if you have a correlation coefficient of 1, then every point is on the line, on a line. So there's a perfect linear relationship between the variables. Correlations are always 1 or less. Okay. So correlation is going to be between 0 and 1. The correlation between the heights of identical twins is around 0.95. Interesting. The correlation between the heights of identical twins is around 0.95. What they're saying is you take data for identical twins, height data, and you just, okay, this is twin 1 and twin 2. They're both identical twins, and you plot the heights. Well, you would expect in this case, you actually would expect to be following a a correlation of a 45-degree line because the height of twin 1 is going to be equal to the height of twin 2. But again, I just want to point out the correlation coefficient isn't about just a 45-degree line. It's any line, but in this case, it would be 45-degree. And they're saying that if you take a lot of data and plot this, you're going to get identical twins are going to be highly correlated, have a high correlation coefficient, 0.95. That makes sense, right? Identical twins are like this. It's like they're the same. They look the same from a physical standpoint, almost identical. But it's not perfect, though. It's 0.95. A scatter diagram for the twins would look about the same. Identical twins are like each other in height, and their points in a scatter diagram are fairly close to the line y is equal to x. However, such twins do not have exactly the same height. That is what the scatter around the 45-degree line shows. So do they have a graph they gave us here? I guess not, but okay, we can imagine what this would be. Again, something like around the line y is equal to x, just really hugging 0.95 would look like that. For another example, in the U.S. in 2005, the correlation between income and education was 0.07 for men aged 18 to 24, rising to 0.43 for men aged 55 to 64. As the scatter diagrams in Figure 6 indicate, the relationship between income and education is stronger for the older men, but it is still quite rough. Weak associations are common in social science studies, 0.3 to 0.7 being the usual range for R in many fields. So Figure 6 here has nothing to do with these income levels. The Figure 6 is just a reference for different types of correlation coefficients. So it's just saying that there's another example where in the U.S. in 2005, the correlation between income and education was really low for men age 18 to 24. And why does this make sense? Because you can have, if we come here, okay, here's a low, or, okay, well, yeah, let's stay here. This is 0.07 is closer to 0. So income level in education, if this is income level in education, well, men 18 to 24, you have guys that they professional basketball players making millions. You have, there's people that don't go to college, they get into real estate, right? You have all kind of stuff going on. There's no, I mean, if anything, maybe it would be correlated that the education level is low, but the income level is high, but actually not really. Yeah, you would presumably have more lower education people making higher income. That's true, because the people that are going to college aren't making the income yet. But then you're also going to have that's what's going to happen. You're going to have a mixture of, actually, you would think it would be that since the education level is low from 18 to 24 in general, that the income level would be low, but you do have some getting out of school and going into like the oil field making money. So it's going to be all over the place. There's no way that the association is low in the sense that if I told you, here's the education level of somebody 18 to 24, I can predict the income level. Well, I don't know. I mean, I might have no idea if I'm dealing with someone that went into the oil field, is in college, is a professional basketball player. So it's going to be hard to predict, right? However, as the age goes up, for ages 55 to 64, the correlation goes up to around 0.43. Now, why is this the case? Because at 18 to 24, you don't have any college graduates, right? You don't at 55. Okay, like at 55 to 64, if you have college graduates or people that are going to college, plan to go to college, well, they're already established in their fields now. They're working, right? With 18 to 24, you have people that are deciding to go to college, but their income levels are low because they haven't gotten their degrees yet. They haven't gotten into their field yet. 55 to 64, it makes more sense if they've got this education, college degree. Well, but then they've gone to the workforce. They've gotten promoted, right? It's more predictable. It's more predictable to say, look, if you're in the age 55 to 64 and you have a college degree or a master's degree, well, then you've probably gotten a good job and you've been working in your field, right? And your income level's high. as opposed to 18 to 24. If you're deciding to go to college and go the whole college education route, that's fine, but your income level's still all over the place. Here, it's more stable. It makes a lot more sense to say, look, what's the education? If the education's high, then in general, I can tell you the income's going to be higher. It's more predictable. So the relationship between income and education is stronger for the older men, but it is still quite rough. It's still quite rough, right? I mean, you could still have professional basketball players that even though they've retired, they're millionaires, billionaires, their education's low. It's still rough, but the correlation's stronger. Weak associations are common in social science studies, 0.3 to 0.7 being the usual range for R in many fields. Interesting. Social science studies. A word of warning. R is equal to 0.80 does not mean that 80% of the points are tightly clustered around a line, nor does it indicate twice as much linearity as R is equal to 0.40. Right now, there is no direct way to interpret the exact numerical value of the correlation coefficient. That will be done in chapters 10 and 11. Okay, so we're not going to make any assumptions about, okay, if you have twice as large of a correlation coefficient, that means we don't know what that means, right? It doesn't mean that R is equal to 0.8 doesn't mean that 80% of the points are tightly clustered around a line. Comparing R is equal to 0.8 to 0.4 doesn't mean, twice as much of a linear fit. I mean, it's just twice as much of a correlation coefficient value. That's all we know. We're going to analyze the meaning of the correlation coefficient numerically in upcoming chapters. Okay. So far, only positive association has been discussed. Negative association is indicated by a negative sign in the correlation coefficient. Okay, so we can't have negative correlations. That's going to indicate a negatively sloped line. So with that, then the correlation coefficient is going to be between -1 and 1. Figure 7 shows 6 more scatter diagrams for hypothetical data, each with 50 points. They are scaled just like figure 6, each variable having an average of 3 and a standard deviation of 1. A correlation of -0.90, for instance, indicates the same degree of clustering as one of positive 0.90, but with the negative sign, the clustering is around a line which slopes down. With a positive sign, the line slopes up. For women aged 25 to 39 in the U.S. in 2005, the correlation between education and number of children was about -0.2, a weak negative association. A perfect negative correlation of -1 indicates that all points lie on a line which slopes down. Okay, so the magnitude of the correlation coefficient, the magnitude, so disregarding the sign, indicates the strength of the association from around a line, any line oriented in any way, not just a 45-degree line. The only thing the negative and the positive is telling you is if the line is negatively sloped or positively sloped. That's it. So if we come to figure 7. So here's this is similar to figure 6 in that all of these have the same point of averages and the same standard deviations, vertical and horizontal, but now it's getting more and more. It starts off as the magnitude of the correlation coefficient is low, and then the magnitude gets higher and higher in the negative direction until you're getting close to 1 here, or close to -1 here. But if this was positive 0.99, the idea is it would be the exact same hugging about a line, just this would be plus 0.99 correlation coefficient. It's like the exact same data, just now it's sloping upward instead of downward. Okay, so correlations are always between -1 and 1, but can take any value in between. A positive correlation means that the cloud slopes up. As one variable increases, so does the other. A negative correlation means that the cloud slopes down. As one variable increases, the other decreases. In a real data set, both standard deviations will be positive. As a technical matter, if either standard deviation is 0, there's no good way to define the correlation coefficient. Right, because what they're saying here is that, so in a real data set, both standard deviations will be positive in general, right? But if you have either standard deviation is 0, well then, okay, that's an issue because If you have a standard deviation of 0, let's say in the vertical direction, well, then all the data points are going to be on a horizontal line because there's no standard deviations. Does that mean it has a perfect correlation coefficient? You can't really say that, right? Think about it. So if the standard deviation in the vertical direction was 0, that literally means that the data points have to be on some horizontal line somewhere. They can be spread out horizontally, but there's no spread vertically. So does that mean that the correlation coefficient is perfect? I guess you can't really say that. So there's no real way to define a correlation coefficient if you have either of the standard deviations in the horizontal vertical direction or 0.